Hello and welcome. This is Chapter 8, Section 2 on uniform circular motion. We're going to set up some new coordinate systems and new ways of thinking about it to analyze the dynamics of particles that move in a circle at constant speed. And so, as this slide says, we introduced the kinematics of uniform circular motion in Chapter 4. Chapter 4 introduced the period of motion, and then period and speed in a circle is typically the first thing that you encounter, and then you define angular position, and that gives you, angular position is the coordinate that allows you to treat uniform circular motion or particles moving in a circle with one parameter. It's almost like a particle moving in a straight line at constant speed. Uniform circular motion is a particle moving with a constant angular velocity. And sure enough, we define angular velocity omega to be d theta dt. And later in the chapter, we derived the concept of centripetal acceleration. That's the thing that's important here, because the formula for centripetal acceleration, there's two forms. It's either speed squared over the radius, or it's rate of rotation squared times the radius, rate of rotation being omega. And it's always directed towards the center. And this is the chapter where we really confront this issue of feeling thrown out from a circle when we're actually accelerating towards the center. But we start with this idea of a simple coordinate system. We use what's called an RTZ coordinate system, and different problems in the book will use different planes of this RTZ coordinate system. So imagine a coordinate system where you have the axis is kind of off to the side of the circle, and the r-axis is defined to point inward towards the origin. It's not very standard, but this is the one we're using. So the r-axis is the direction of the positivity for the r-axis is one that points inward towards the origin. The z-axis is, well, let's do the t-axis. The t-axis is the axis that's tangent to the motion. So as you can tell, like if it's a circle, then the velocity is going to be in the t direction. And then finally, a z-axis is perpendicular to both of those, which the z-axis will be more useful than you think. Especially when we get to vertical circles. So we have an RTZ coordinate system, and it allows us to reframe some of these quantities in terms of these components. Something not in the textbook, but a useful remark is that some folks might confuse this with the so-called cylindrical coordinate system. And the cylindrical coordinate system is different, or cylindrical coordinates. It's different because there's an angle. One of the coordinates is an angle. There's no angle in this system. And also the cylindrical coordinate system isn't moving. It's not a rotating coordinate system. It's just a static coordinate system where every point in three-dimensional space is characterized by its distance from an axis and its angle from another axis and its height, the r theta z, for instance. And there's also what are called rotating coordinate systems, where the origin is fixed in a spot, usually at the center, and the axes just kind of flip like blades of a ceiling fan or parts of a windmill. But that's not what we have. And this is really the only place where I've seen this coordinate system, but it's useful to solve the problem. So in looking at this coordinate system, we can reframe our important kinematic variables in terms of their components in this coordinate system. For instance, moving in a circle, you're not moving towards or away from the r axis. And so v sub r is 0, v sub z is also 0. So all of the velocity is fixed on this t axis. So we call v sub t the tangential velocity. And as we showed in chapter 4, the tangential velocity is proportional to the rate of rotation times the actual radius itself, omega being d theta dt, the angular velocity. And this is a common theme in physics, that most of these linear quantities have a rotational equivalent. Also, we can constrain the acceleration to the r-axis. And we have two different ways of saying that. It's v squared over r or omega squared r. And then a sub t is 0. A sub t is 0 unless the particle is increasing or decreasing speed. Then that will be non-zero. That's addressed in the final section of this chapter. A sub z is also always, like v sub z, it's always 0. It's defined to be, at least it's defined to be 0. So that's our useful coordinate system for velocity and acceleration. Well, this is a quick check question that you might encounter in the, okay. So the physics of this uniform circular motion chapter is that the net force points towards the center. And it's the best way to learn this is to just go through a bunch of different examples of how the forces, either a component of the force or total two forces themselves or a single force, contribute to this centripetal acceleration. The book doesn't use the term centripetal force. And the reason for that is it's still a force. And from their research in this development of this book, they found that when you use the term centripetal force, often it leads people to think that there's a centripetal agent. There's some centripetal thing doing the pulling. When really all these examples are just forces that we know already. The normal force, the tension force, gravity, sometimes friction. And so this is the formula for the net force in uniform circular motion. So you can see why this, and this is exactly what I just said, that you can see how the centripetal acceleration is caused by a force that we already know. And so it looks like have Newton's second law is also constrained in that single direction, in the r direction. It's not in the t direction, and it's not in the z direction. Again, the only way it would be in the t direction is if the particle was speeding up or slowing down. Usually it's not. Let's skip that. So here's a typical example of these calculations, turning a corner. So as you imagine taking a corner at an intersection at a constant speed, what are all the forces acting on you? Well, you got gravity pointing down and normal force pointing up as usual in the z direction. But if you look at the figure, you see that the force that is pushing you towards the center, looking at the tires, is actually static friction force, because it's a static friction between the road pushing the tire perpendicular to the direction of motion. And this is a perfectly good example. We got a nice free body diagram right here on the lower right hand side. Note the directions of the axes. Typically we'll draw the r axis to the left if it's to the right of the figure, and z is always up. The t axis becomes useful in vertical circular motion. And so F net literally does point in the r direction. But as this car rotates, this free body diagram rotates with it. So static friction is the force responsible for the car turning a corner. And you can do problems such as like how fast can you turn the corner given a radius. Typically it's pretty alarming. It ends up only being like 10 or 15 or 20 miles an hour. And as far as slipping goes, it doesn't sound very realistic, but by slipping, we usually mean the car's brakes are starting to screech. I mean, you're putting the system under tremendous stress. So moving on. Skip that. What about banked curves then? Now, banked curves are interesting because you don't actually need friction for the car to make that turn. It's only the normal force, and there's several remarks to make about banked curves. first of all, the free body diagram, so we're on an incline. And so in chapter 6, you probably did several problems with cars on inclines. Well, in those problems, we weren't worrying about the car. It was always accelerating either up the incline or down the incline. But if you look at this free body diagram on the right, for the banked curve, the acceleration is to the left. It's not up or down the incline. That would be the car kind of skidding as it skidding up or down the incline as it turned the corner. So the force that's responsible for the curve is the normal force. In this case, the normal force has to be bigger than gravity. Because if you look at the diagram, you'll see that the z component, the normal force is not in the z or the r direction. It's still perpendicular to the surface, but neither of our axes are in that direction. So there has to be a single component, the n sub z component of the normal force, that cancels out gravity, which means there needs to be a leftover component in the r direction to provide the acceleration. So the normal force has to be bigger than gravity when you take a banked curve. And when you go through the equations of the banked curve, you'll find that for every angle, for every banking angle of a certain size of a circular track, there's an optimal speed that the car can take the curve without any assistance from friction. If they take the speed too slow, well, then that's not the optimal speed to take it. And so if there was no friction, you can imagine that the car would kind of spiral inward. Oftentimes it's helpful to, instead of thinking of like banked curves, to think of, and I got enough space for this, so I might draw this out here. So if we look at, instead of banked curves, if we instead think of a circle, little marble or something rotating on a cone, right? What we'll see is that for every distance from the edge of the, from the edge of the cone to the, undo that, just a minute. Okay. The banked curves analysis says that at a specific radius, right? At a specific radius, you're guaranteed, you have to have some constant speed to take this curve without the edge of friction. So if your speed decreases, what you'll observe is that on a frictionless cone, the thing's going to spiral inward. Right? Spiral inward slower and slower. And then on the opposite side, if you take it too quickly, if you take, because the radius, as the radius gets smaller, the speed required also gets smaller without friction. So you take it faster and faster, then you'll start to spiral outward. And that's well, you'll spiral outward still on the surface of the cone, right? Okay, sorry, this drawing isn't great. But so if you're not at that exact speed needed at that banking angle and radius, which, by the way, that speed is square root of r times g times tangent theta, where theta is given with respect to the horizontal. If you're not at that exact speed for that angle and radius combination, well, without friction, you're going to spiral inward or spiral outward. It's called inspiron. That's things that these black holes did several years ago. Well, billions of years ago, but several years ago, when they discovered gravitational waves, they had found an energy signature from two black holes that had collided by spiraling inwards. It's called inspiron. Anyway, off topic, but interesting. So if the car is moving too slowly, if the car is moving too slowly, now the surface has to push up on the lateral direction of the car in order, with the static friction force, to keep the car from to maintain that circular path. And usually your instructor might want to explore this in a more detailed exercise, but typically for typical highway setups like rubber on concrete, the coefficient of friction is static friction is about 1. So that means any angles less than, say, 45 degrees, tangent of 1, there's no minimum speed that you have to maintain in order to keep from spiraling inward. Now, if you were at a banking angle of like 60 or 70 degrees, then you would have a minimum speed. We'll erase this. One. Okay. Now, this is the scary one. If you are you taking it too quickly, then the surface has to push you down. The banking angle has to push you down to keep you from skidding upward. So to keep you from veering up the incline. So say if I have, for instance, just set this up again. Oops, set this up. All right, let's say I got a banking angle like this, and it's a 2-lane highway. So the third thing, or the thing up here. And so if you got the car, we love to kid around about how bad the drawings get when we're doing 3D physics. But if the car is taking it at a velocity, if the velocity is bigger than square root RG tangent theta, which again you derive in the bank curve section, it's not going to stay in its lane. It's going to start to skid upward, skid upward, skid upward. There won't be enough force to keep it in that circular path. And unfortunately for typical highways, there is a maximum speed with which you can take this before you do start to skid. Fortunately, these maximum speeds tend to be a bit outside of what you can usually do in a typical car, but they are there. And then conversely, if you're like in a motorcycle thing, like a very steep banking angle, like some amusement park or those like motorcycle globes where they go motorcycles inside the globes. If it's a steep enough banking angle, then there's no maximum speed. So it's a really interesting topic. But there's many different examples of uniform circular motion, and sometimes the most difficult part is the reasoning of these problems, just to make sure that you understand, because in this case, the net force when the car is taking the curve at greater than the optimal speed, the normal force is bigger because now the upward component of normal has to equal not only a downward gravity, but also now a downward component of static friction. And the R component of normal now adds with the R component of static friction to give a bigger net force. So it's not just a single force, for instance, that is responsible for these accelerations. In this case, it's a sum of components of two separate forces that are related, actually, that gives us this net force. So yeah, several different examples involving circular motion. Bank curves are just a common example. Really, really good practice with reasoning. And we'll continue to talk about cars on hills and valleys and the loop-the-loop and roller coaster in some future videos. But that's enough for this video for now. I appreciate your time. And in the next video, we'll talk about, I think, orbits, which is always a fun topic. Thanks for your time. Take care.